in general, if you have a non-zero concentration flowing in, then you're going to have the term C times Rn, giving you the rate at which solute is flowing into the system. And then you'll have minus your concentration in the system times your rate of flow out. And that'll be your dq dt. Now I said here, assume V of t is constant. I don't really want to assume that until I get over here, because there's no reason to assume it at this point. So we're going to, it'd be nice if we had chalk that was right. Let's see. Other end goes better. Okay. Now, this equation can be written the same as it is, except using q prime for dq dt, so that we can, by analogy, say that this equation turns out to be of the same form as your general non-homogeneous linear equation. Okay, y prime plus p of t y equals q of t. And this, as we recall, is easily enough solved. You use integrating factor. Well, okay, first of all, just to build the thing up, this equation, the homogeneous equation with 0 here instead of some little q of t, has solution y equals a e to the negative p of t, capital P of t, where capital P prime is equal to little p, and we easily, and we did this a couple of weeks ago, we easily verify that this would then be a solution to this equation with the 0. So that y prime plus p of t y equals q of t, it being the non-homogeneous equation, well, if we multiply both sides by a term very similar to this one, but we're going to make it e to the p of t, capital P of t, where capital P of t again is equal to, where the derivative of capital T is the little p function, then we get this equation here, okay, with an e to the p of t in front of every term. Well, the left-hand side of the equation is just the derivative of y equals e to the capital P of t, as you can easily verify, and as we did a couple of weeks ago. I'm not going to go over it again. And that's going to equal e to the capital P of t times q of t. And the solution of the equation is then the integral, integrate both sides with respect to t. The integral of this one, this being the derivative with respect to t, is just y e to the big P of t. And the right-hand side is just the integral of whatever e to the capital P of t, q of t function is. So there we have it. And then plus an integration constant. So that y equals, well, this divided by your e to the p of t, big P of t. And I didn't write that correctly. I threw the integration constant in there a little bit late. The k being part of the right-hand side is also divided by e to the capital P of t. I did that when I did it down here, but I didn't write it correctly here. Okay, now, just in the case of a constant v, because you don't know well, there's a connection I haven't made, so I've got to go back with it. Okay, so for constant, we're going to do this. We're going to now do this equation for constant v. And it should be clear that q is going to take the place of y here. Okay, you're going to bring this term over onto the left side so that your p of t will just be your q over v times r out. It will just be your r out over v. The y will be your q. And the little q of t will be your big Q of t. No, sorry, your little q of t will be c times Rn. So making those correspondences, we see that our equation can be written in this form, whether you see that correspondence or not. Okay. For constant v, our equation would become this. And then we rearrange the q over v times r out term this way so that we definitely see the form of the linear equation. The solution to this equation is then going to be, just by analogy with what we did here, you're going to essentially multiply both sides by e to the r out over v. That's going to be your p of t function. And then integrate both sides, and you're going to get this. And I wrote my k wrong here. I finally wrote it correctly down here. Let's get it right here, plus k. So we go through the same steps we would go through here, and just by analogy with what we have up here, this is the solution we get. And of course now, our integral of e to the r out over v, which we could not just go ahead and do if our v function wasn't constant. If this is a function of t, then the integral gets a lot more complicated. And sometimes we can do it, sometimes we can't. But anyhow, if v is constant, this is what we have. And it simplifies to this, and I'm not going to go over the details of it. It's very straightforward. You just got to keep track of your variables. And if you're used to doing these equations, you can easily do this one. Now, one additional comment I'll make is that if v is constant, you don't really need to even do this. You can do this simply by separating the variables, because there's no t dependence on this side. So you just get dq over this whole thing equals 1, and you go from there. And then see if that doesn't correspond to the form of the solution that we get here.